Hi guys, welcome back to another video of me teaching, and today I have this question on the board for you guys. So why don't we just get into question? Well, this question is a bit complicated, right? But it is actually not that complicated. So once you've read the question, because I'm not going to read all of this out, then you think, can we solve this using induction? Well, let's try. If we try and use the traditional induction, we see that step 1 is always to prove true for the base case, which here is n equals 2, which is true because it's already given. And then step 2 is to assume true that n equals to k. And step 3 is to prove that it is true when n is equal to k plus 1. But actually, step 3 is very, very hard or near impossible. You can try yourself, but I'm not going to do it in this video. So an example of how step 3 is very hard. It is even very, very hard to prove from n equals to 2 to prove n equals to 3 is true. It's still very hard. So in our video, I'm going to do something called the backwards induction, where we want to prove it is true when n is k minus 1. Now, some of you guys might be thinking, why would we do this? This makes no sense. For example, if k is 100, then we can only prove it is true for numbers less than 100. But what about the numbers greater than 100? Well, we have a way of solving this. As long as k is a very, very, very big number, and it can be as big as we wish, then this seems to have a bit of logic into it. So, why don't we refine our base case a bit? I'm going to refine our base case to let it be so that n be 2 to the power of m. Because now we can decide our k to be very, very big. So if I redo the base case for n equals to 2 to the m, then we see step 1 will be to prove true when m is equal to 1, or in our case n is equal to 2. And of course this is true because this is given. And then step 2 is we assume true for m is equal to k. So n is equal to 2 to the power of k. And then step 3 is we have to prove true. And in this thing, we're going to use traditional induction. We have to prove for m equals to k plus 1, or n is equal to 2 to the power of k plus 1. Okay, so how do we prove this? Well, the first thing I'm going to do is I'm going to write this out. So it will just be just like this. And then we have to prove it is true for when m is k plus 1. So I'm first going to write what the left-hand side will look like. So the left-hand side will just be this, and if we sub everything in, okay, so this is the left-hand side. Well, let's see. This 2 to the power of k plus 1 is just equal to 2 to the power of k times 2. So we see in here, the basic logic is we're just dividing by 2, technically. So why don't we use that here? Since this is 2 to the power of k plus 1, we can obviously change that into 2 to the power of k times 2. So if we can split this up like this into 2 different fractions with 2 to the power of k on the denominator, then we can divide both of these fractions by 2. So we can still use this formula. So that is actually what I'm going to do. So this is equal to f of, okay, big brackets, and then the inside will be first this over 2 to the power of k, and then we add this over 2 to the power of k, and then we need the whole thing over 2. And now this is back to our given information, so we can use this again. So now I can change this into this. So if I write it down here, then the top will be f of this and then we add f of this and then we over 2. Okay, now that we have this, I'm going to use this formula to change this and this. So if I go back up here, then we see this will equal to, the top will be that. So you change this into that. So and then we add this, go to that. And then all of this over 2. So now if we change this back, so this becomes 2 to the power of k plus 1. Now you see that now we have proved it. Okay, so now that we know that it is true for n is equal to 2 to the power of m, and we know that it is true for n, we have to prove that it is true for n minus 1. So how do we do that? Well, a very common way of changing this n to n minus 1 is we let the last term to be the average of all of the terms behind it. So if I rub this out, then we see that this will just be, or we just let xn to be the average of all the items behind it. So x1 all the way to xn minus 1 over n minus 1. And then we sub this back into, so it becomes f of x1 plus all the way to xn minus 1. And then we add this. And we can actually do this because it says for any xi. And we have to do over and. Okay, so now if we let this whole thing, we pretend that it is just one number, then I'm just going to give you a little demo. If this was a, then let's see what will happen. So a plus a over n minus 1. This will actually just equal to a times n over n minus 1. And you can try this on your own. So this in mind, now we can change this. So this is equal to f of the a, which is this, and then we multiply by n over n minus 1. And then the bottom is n. And now we have changed the denominator from n to n minus 1, because now cancel, and we can put this on the bottom. So this is n minus 1, and this term is gone. Okay, so now that we've changed the left-hand side, then now we can change the right-hand side. So this will be equal to, if you just look over here, f of x to the f of xn is this. So now, the first thing I'm going to do is I'm just going to do a little bit of this. Okay, so if you notice, on the left-hand side and on the right-hand side, we have this term. And this term is the same as this term. Now, the reason I drew those brackets was because if you do this in your head, you do partial fractions, then you move this part to the left-hand side and do some basic algebra, then you can see that we'll have the equation n minus 1 over n times f of this is just equal to this over n. And now we see that the n and the n cancel, and we can bring the n minus 1 to the denominator. So this term is gone, and this denominator becomes n minus 1. And now look, we've proved it for n minus 1. So this is the final answer for this very fun backwards induction problem. So thank you guys so much for watching, and if you enjoy my video and you want more videos like this, please consider liking and subscribing. If you want to master something, teach it.